maybe? Yes, good. It's really a pleasure to be back here. As you have said, I've been in the field for a long time. I think the first time I gave a talk in this room, which existed at that time already, it was in 1986, I think. So I don't think any of you were present. You were there in 1986? Okay, good. So Gerhard, we are the two dinosaurs of this audience. Okay. Okay, so yes, and it's always fascinating to come back here. I mean, I've been here several times, and it's to see the progress that are coming from this institute is just impressive. Okay, so today I've decided to give a talk which looks a bit like a textbook talk, in the sense that I would like to address textbook concepts, the concepts of coherence or long-range order, if you prefer, and the concept of superfluidity. And the reason for which I want to do that is that in several textbooks, especially those which were written in the pre-quantum gas era, these concepts are really mixed. And I think now with the work, in particular with quantum gases, the distinction between the two concepts is becoming clearer and clearer. And my talk is just about that. How can we discriminate between these two concepts? When do they overlap? When are they different? So, as you know, we have been celebrating this year the 100th anniversary of quantum mechanics, at least quantum mechanics as we use it every day. And among the things that happened 100 years ago, there is this famous paper by Einstein, which was following a work by Bose. The work by Bose was on photons. Einstein transposed the work of Bose to matter, and he discovered what we now all know, which is Bose-Einstein condensation. Einstein called it the saturated ideal gas because he was dealing with a system where there was no interaction. But of course, it was later generalized to interacting systems. So from a theory point of view, this was really the first step in quantum matter. Actually, quantum matter already existed in labs in 1925, since it was in 1911 that Kamerlingh-Onnes, in his lab, had discovered superconductivity. At that time, the connection with quantum mechanics was not done, but still, Kamerlingh-Onnes had found that below a certain temperature, some metals and then some alloys could conduct electricity without any resistance. And the Nobel Prize that Kamerlingh-Onnes got in 1913 makes explicit mention of that. The Nobel Committee said that they give the prize not only for liquefying liquid helium, which was a major achievement, but also, that's why it's put inter alia, but also to other things that were discovered at low temperature. And I like the picture which is on the right here, because on this picture, you see already a connection between quantum physics and low temperature physics, since you have on the same picture Kamerlingh-Onnes, and you have Ehrenfest and Bohr, who are the young quantum physicists of that period, ready to find new stuff. Okay, just a jump in history. Let's look at quantum matter still before 1940. So it was in 1938 that the superfluidity of liquid helium was discovered. It was a back-to-back publication between Kapitsa in Moscow and Allen and Misner in Cambridge. And they found that, a bit like in a superconductor, the viscosity is reduced very much below some threshold. And actually, Kapitsa coined at that time the term superfluid, just by analogy with superconductivity. He said the present limit perhaps is sufficient to suggest that, by analogy with superconductors, that helium between the Lambda point enters a state called superfluid. Okay, and it was not long after that. It was the work of Landon and Tisa, and then Landau, but mainly Landon and Tisa, to connect this Bose-Einstein, to connect the superfluidity of liquid helium to Bose-Einstein condensation. And since that time, superfluidity and Bose-Einstein condensation have been linked in some way. This is what I wrote here. Since the early days of this quantum matter, Bose-Einstein condensation, that is macroscopic coherence, I will come back to that in a moment, has been considered as synonymous with superfluidity in many textbooks. And the goal of my talk is really to question this equivalence. So first of all, I would like to give you, to remind you the definition of condensed fraction and superfluid fraction, just to tell you that these are not the same objects. And then I would like to address two questions, which are symmetric with respect to each other. First, can there be full superfluidity with no or with very little coherence? And then can there be full coherence with no or little superfluidity? And then I will spend more time on the point 3 than on point 2, and I will give you some experimental test of this last point. Okay, so first let me start with the definition of condensed fraction and superfluid fraction. And I should say that if you have any question during the talk, don't hesitate to raise your hand. I will be happy to take it if something is unclear. So let's start with the definition of condensed fraction. The way one defines the condensed fraction is to use the one-body density operator. So you start with a fluid with n interacting particles. They can be at 0 temperature, at finite temperature. There is to describe this system by a n-body density operator. And you construct an object, which is a one-body density operator, by tracing over n-1 particle. So you are left with a rho 1 here. And this rho 1, you can characterize it by calculating its matrix element between position R and position R prime. This is simply the trace of psi dagger R, which creates a particle in R, psi of R prime, which destroys a particle in R, trace of this times rho. And once you know this operator rho 1, you can calculate all one-body observable. So you can calculate, of course, the spatial distribution, just take the diagonal part, rho 1 between R and R. But you can also make a Fourier transform with respect to the distance R minus R prime, and then you will get the momentum distribution. So you can get all one-body observable. Of course, you don't get access to correlation between particles. When you have only rho 1, you don't have access to density fluctuation, for example. Now, how do you define the condensate? You define the condensate using rho 1. That is, rho 1 is a Hermitian operator, so you can diagonalize it. You can rank its eigenvalues, like what I have done here, starting with the largest here and then the next one and so on. So the sum of all eigenvalues is capital N, the number of particles in the sample. Every eigenvalue is positive. And if you denote pi 0, the largest eigenvalue, the one which is sitting here, then, and you call psi 0 the corresponding eigenfunction, then one say that you have Bose-Einstein condensation if this largest eigenvalue is macroscopic, in the sense that it is of order n when the number of particles tends to infinity. So condensate means that you have a macroscopic population of a single particle state, psi 0. And then pi 0 is called the condensed fraction, and so on. Note that usually there is only either 0 macroscopic eigenvalue, then you have no condensate, or you have one macroscopic eigenvalue. And there is a good argument for that, which was given by Nozière a long time ago. There are still a few systems where you can have a few macroscopic eigenvalues. They are quite difficult to achieve, those systems, but I have given you here an example of such a system, which was a spin-1 gas with antiferromatic interaction that we studied together with Evra Arcu and Fabrice Gerbier, and which we published a few years ago. But in all the talk here, I will have only one macroscopic eigenvalue for the rest of what I will discuss. Now, something which comes directly from condensation is long-range order, at least if you take a system confined in a box, so flat system, take periodic boundary condition, then simply by symmetry argument, if you have a condensate, by symmetry argument, the wave function of this condensate has to be simply 1 over the square root of the volume of the box. And therefore, if you look at the one-body correlation function, G1, which is defined with atoms exactly in the same way as in quantum optics, then it's relatively easy to show that this G1 will tend to a non-zero value when the point R and R prime gets further and further away from each other. For that, you simply decompose. So I have to get used to this pointer. Well, never mind. You decompose rho 1 on the basis on the. Can I do it? Yes. you decompose rho 1 on this eigenvalue basis. So pi j again are the eigenvalues, pi j are the eigenstates. And when you take this in sandwich between R and R prime, you get first the contribution of the largest eigenvalue pi 0 plus the sum over all other eigenvalues. So the contribution of pi 0, since psi 0 of R and psi 0 of R prime are uniform, will give you simply pi 0 over L cube. And the other terms correspond to a superposition of many oscillator terms, which will tend to 0 if R and R prime become very far from each other. So in the end, when I take the limit of R to R minus R prime going to infinity, I get a non-zero value for G1. And so this is what is called non-diagonal long-range order. So condensation and long-range order amounts to the same thing. And this can be tested with atoms using matter wave interferences, for example. Now, what about the superfluid fraction? So if you ask to someone what is the superfluid fraction, you will get two different answers depending whether you ask to an experimentalist or to a theorist. If you ask to an experimentalist, usually probably the answer that you will get, especially if you are asking the question to someone from the helium community, will be the following. Let's work in 2D for simplicity. You suppose that you put your 2D gas on the surface of a substrate, which is a cylinder. And then you start to rotate very gently this cylinder, and you look at the film of atoms that you have put on the cylinder, and you ask yourself, is the film rotating or not? And what will happen is that a fraction of the film will rotate, and a fraction of the film will not rotate. More specifically, the surface, the substrate has some roughness, and therefore, when you start to rotate gently the cylinder, the normal part of the fluid, the part which is not superfluid, will be dragged, will be set into motion by the motion of the substrate, whereas the superfluid will prefer to stay at rest in the lab frame. So the superfluid fraction in this experiment corresponds to the fraction of the fluid that doesn't want to move with the substrate, and that you can measure by measuring the moment of inertia of your cylinder, and the moment of inertia is reduced with respect to what you would get if everything was rotating with the substrate. Now, if you go to a theorist and ask how do you get the superfluid fraction, then the answer is very different at first sight, at least. The answer is to make something which is a concept experiment. Suppose that you don't work with periodic boundary condition, but you twist slightly gently by a very small angle the boundary condition. That is, if you consider here psi of x for the jth particle, psi of xj plus the size of your box, it has to be now with a twisted boundary condition e to the I theta times the initial wave function. When you do that, and if you calculate the energy, say, of the ground state, if you are at 0 temperature, or you calculate the free energy if you are at non-zero temperature, you will get some increase of energy with respect to non-twisted boundary condition. Just by symmetry reason, this increase of energy will be quadratic in theta. And the superfluid fraction is simply the prefactor here times some constant for coming from the h bar and the atomic mass. So the superfluid fraction is the cost of energy for twisting boundary condition. And now you may say, what are these two definitions? How do they connect? Actually, the connection is very simple. The connection is simply due to the Sagnac effect. When you have this rotating cylinder, and if you go in the frame where in the rotating frame, you rotate together with the cylinder, then what appears in this rotating frame is the so-called Sagnac phase. This is the Sagnac phase that is used in gyro lasers, for example. And therefore, if you are doing physics in rotating frame, you do not have periodic boundary condition anymore. You have some twist, which is simply proportional to the rotation of your frame. And so if you are sitting in this rotating frame, actually you have the normal fluid, which is at rest with you because you are rotating together with the cylinder, and the superfluid is rotating with respect to you because it is at rest in the lab frame. So it is rotating with respect to you at a frequency minus omega. And so this increase of energy that you measure when you twist the boundary condition is nothing but the kinetic energy of the superfluid fraction measured in the rotating frame. And so the two point of view really coincide. And if you want to know more about that, I refer you to the review paper we wrote together with Emmanuel and with Vili, where this is explained in detail in appendix that was written by Vili. Okay, so how do you access the superfluid density? So you can do this measurement of the moment of inertia. Another way is to look at sound propagation in the medium. Let's suppose that I'm at T equals 0, 0 temperature for simplicity, so that the normal fraction in my medium doesn't move. It is pinned by the irregularity of the substrate. This corresponds to the dark little oscillation on the picture here. And I look at the propagation of a sound wave in this medium with a wavelength for the sound, which is much larger than the typical length scale for the defects of the substrate. And then I look at the speed of sound in this medium, and you can relate the speed of sound to the superfluid fraction by the simple formula. The superfluid fraction Fs is simply kappa being the compressibility of the cloud, times mc squared. So the compressibility is just the derivative of the density of the fluid with respect to the chemical potential. So if you can measure the compressibility on the one hand and the speed of sound on the other hand, you will see an example of that later, you have access to the superfluid fraction. Now, here I have assumed that the normal fraction doesn't move. If you are at non-zero temperature, then the normal fluid can move, and the situation is more complex because then you have two sounds. You have probably heard about first sound and second sound in helium because the two fluids can move. So it's more complicated. But at T equals 0, the situation is very simple, and you have the formula written on this graph. Okay, so now I have defined my two fractions, the condensed fraction on the one hand and the superfluid fraction on the other hand. And so now let's look for situations where these two quantities can differ. And as you will see, they can differ a lot. So first, can there question? Is it always obvious what mass to put? You have pairing? Oh, yeah, then yes. So if you have Cooper pairs, you should put 2m, at least in a simple point of view. But here I'm addressing simple atoms, so there is no question. Yes, for sure. Yeah. So first question: can we have full superfluidity with no or with little coherence? The answer is yes, and there are a few examples of that in nature. The first one is about 2D systems. If you take a 2D Bose gas at non-zero temperature, then it is known, since the work of Kosterlitz and Taules, following some work by Berezensky, that you can have a superfluid transition. That is, if you take a 2D Bose gas and you cool it below some threshold, that is, if your phase space density is large enough, then you will have a transition from normal to superfluid. That is, you will have a non-zero superfluid fraction. However, it is also known, since Mermin, Wagner, and Hohenberg, that there cannot be any long-range order in an infinite 2D system, at least if you have only short-range interaction. That is, if you take a 2D Bose gas, then the matrix element of ρ1, the one-body density matrix between n, r, and r prime, has to tend to 0 when r minus r primes tend to infinity. And the reason for that, which is true also in 1D, the reason for that is that when you are in a low-dimensional system, like 1D or 2D, you don't have enough neighbors to maintain a global coherence over the whole sample. That is, you can start to distort the phase from one place to the next without paying too much energy, and therefore you don't succeed, at least if the temperature is not strictly 0, you don't succeed in maintaining the same phase over your 2D plane of atoms. So first example of a system where you can have full superfluidity if you push the temperature low enough, but no long-range coherence, no condensed fraction. Another example in 3D is superfluid helium. If you take superfluid liquid helium, so it is superfluid, and the superfluid density goes to 1, well, the superfluid fraction goes to 1 when the temperature goes to 0, but the condensation, if it exists, is marginal. This is still a bit controversial, whether there is a condensate in liquid helium, but at least if there is a condensate, it's only 7% of the particle which are condensed. These are very difficult measurements. You have to send, the way it is done is to look at neutron diffraction of the sample, and you look at whether there is some part of the atom which are momentum 0 by looking at the distribution of momentum of the diffracted neutron. And the experiment gives a result which is on the order of 7%, not more, which means that 93% of the atoms are not condensed in liquid helium, even though the superfluid fraction, again, is very close to 1. So this is another example where you can have superfluidity without coherence. So just to tell you that sometimes you can have both. I mean, we know that if we take a weakly interacting dilute Bose gas, then we have Bogolubov theory, which describes very well the sample. And then if we have at low temperature, we have a nearly 100% condensed fraction and nearly 100% superfluid fraction also. So the two concepts are not always orthogonal, but there are some places where they do coincide, but it's not always the case. Okay, so, so the condensed fraction is very close to 100%. The correction are simply due to the so-called Li Wang-Yang term, square root of rho A cube, where A is the scattering length. This has been studied in a nice experiment in the group of Zoranadze-Babic. So now I would like to go to I would say, the main part of what I want to discuss today, which is, can there be full coherence, so full Bose-Einstein condensation, with no or with little superfluidity? And as you will see, the answer is again yes. And this question actually originated in a work by Tony Leggett a long time ago, 1970, in which Tony asked the following question: can a solid be superfluid? That is, can I have some spatial order in my system and at the same time maintain some superfluidity in the system? So to put it with a picture, suppose that you are working at t equals 0 for simplicity. The question is, suppose that all atoms occupy the same one particle state, but this state, psi 0 of r, has some modulation. Okay? Can this system be fully superfluid? I have also 100% superfluid fraction, because here I have assumed that I have 100% condensed fraction since all particles occupy the same state, but can I have 100% superfluid fraction? And actually, as you will see, Tony Leggett answered that the answer is no. As soon as you have some modulation, the superfluid fraction has to be reduced by an amount which can be bounded. And this question has been then on the market, I would say, for a long time. In the beginning of a period 2010, there seemed to have some evidence that solid helium was also superfluid. That is, you could have some modulated density and still some superfluidity. But actually, there was a flaw in the way the superfluid fraction was measured. And now I think it's clear for everyone that solid helium is not superfluid, or at least the superfluid fraction is below something that is measurable. But very recently, coming from the cold atom community, there have been some discovery of supersolids, that is, systems that are indeed modulated in space and at the same time Bose condense. That is, you break simultaneously two symmetries. You break the transactional symmetry by getting the spatial order, and you break the U1 symmetry by having your system which chooses a given phase by condensing. And so the question has re-emerged recently whether such systems can be superfluid. So, as I said, Leggett, in his paper by 1970, was able, by a very simple argument, to give an upper bound on the superfluid fraction that can exist as soon as you have some spatial modulation in the system. So I'm not going to make here the full proof of what Leggett did, but I would like to give you an idea of what he did, because it's really a superb and very elegant way of thinking. His idea was to make a variational approach to this problem. So he is going to take some trial wave functions and prove that the superfluid fraction of the real system is bounded from above using this trial wave function. So how does the proof work? Again, I'm not going to make it in full, but I want to give you a flavor. So you start with a ground state wave function here of your many-body system. The many-body system can be anything: bosons, fermions. It can be strongly interacting, weakly interacting, everything. The only assumption is that this ground state wave function is real. This is really required for the proof, which means that you have no breaking of time reversal symmetry, that all the forces between the particles, the forces do not depend on the velocities between the particles, for example. So this excludes quantum Hall system, but it applies to liquid helium or anything like that. So you assume that the ground state wave function is real. And again, what you want to estimate is the superfluid fraction. So we are going to use what I described before. I'm going to twist the boundary condition and look for the increase of energy when I twist the boundary condition. So actually, if my system is complicated, I don't really know the psi-GS. So I don't know either the ground state of the system once I have twisted the boundary condition. The only thing I know is that I have to pay some energy due to the twisting, and this cost of twisting is proportional to n, to theta square, and to the Fs that I would like to estimate, or at least to which I would like to provide an upper bound. So what Leggett proposed is to say, okay, we don't know psi twisted, but we are going to propose some psi trial. For this psi trial, we are going to calculate the increase of energy, which will be, again, n theta square times Fs trial. And we know from the variational method that the energy that we have to pay for the trial wave function is larger than the true energy that we have to pay for the real wave function. And therefore, delta E twisted is smaller than delta E trial, and therefore Fs, the real Fs that I don't know, will be smaller than the Fs trial that I will be able to calculate. Okay, so this is the spirit of the work by Leggett. So what kind of trial wave function should you take? Well, this is where really Leggett made a kind of stroke of genius. It takes a very simple trial wave function. This trial wave function is the ground state in the absence of twist, again, which is not known, but which will not be required for the estimation of delta E trial, times the phase factor, which is supposed to accommodate for the twisting of the boundary condition. And this phase factor is the simplest you can imagine. It's a one-body effect, so it's e to the I something, which is the sum of single particle term, the same term for each particle, so it's written phi of x, and it depends only on the coordinate x, only on the coordinate along you twist. So you get the same phase factor if you take a slab here in the YZ plane for your system. And the phase twist is taken into account simply by imposing that phi of x plus Lx should be equal to phi of x plus theta, the phase twist that you apply. And with that, Leggett was able to calculate the increase of energy for this trial wave function. That's where it's important to assume that the ground state is real, so that you don't have the calculation is simple. And he was able to put the cost of the twist of the boundary condition in the following way. So it's theta square, as I already said. You have the h bar square over 2m times the size of the box, 1 over L square, 1 over Lx, excuse me. And then you have a factor here, which is 1 divided by the average value of 1 over rho bar of x. So I have to tell you what is rho bar. Rho bar is simply the density integrated along the transverse plane YZ. So it depends only on the coordinate x along the box here. And then what you have to take is to take this quantity, integrate over x, dx over rho bar of x, and with that you form what is called the average value of 1 over rho bar. And this delta E trial, as I said, is an upper bound of what you have to pay in reality if you were to take the real wave function for your system. And so you get an upper bound for your superfluid fraction, Fs, which is a quantity which is dimensionless, which is 1 divided by the average value of rho bar, the average value of 1 over rho bar. And now I'd like to make some comments on that. When you see it the first time, it's a bit shocking. It looks complicated, but I would like to convince you that it's not so complicated. And it's very easy to use. That is, you simply measure the density profile of your system, take a photograph, and then you have this upper bound. You don't have to do any other measurement than simply measuring where your are sitting in your fluid. So some comments on Leggett's inequality. So the first one is a trivial comment. The quantity that appears here, this product of rho bar times 1 over rho bar, is always larger than 1. So the denominator is always larger than 1, which means that the fraction is always below than 1. So it's always a meaningful inequality. What you get is always, I mean, we know that Fs is smaller than 1. It's a fraction. But here we get something which is strictly smaller than 1. So this inequality is always meaningful. I just said strictly smaller than 1. Actually, it can be 1, but only at one condition, if rho bar is uniform. If rho bar is uniform, then the average value of rho bar and the average value of 1 over rho bar is constant. Well, so rho bar is constant, so then you get 1. But as soon as you have any density modulation, then the product rho bar times 1 over rho bar will be strictly above 1. So the dense superfluid fraction will have a bound which is strictly below 1. So any modulation causes a reduction of the superfluid fraction. And maybe I can comment something also, which is the optimal choice that you get for the function phi of x. I tell you that Leggett takes this ansatz where he puts a given phase factor, which is the same for all particles, which is phi of x. And the phi of x that Leggett found, which gives us the tightest bound, is simply d phi over dx. So the derivative of phi is 1 over rho bar of x. What does it mean? It means that if you want to get a very tight bound, the tightest bound possible, you should put large phase gradient where the density is low. So I remind you the rule of the game. Phi of x has to increase between 0 and the phase width theta over the size of your sample. But you are free to arrange this growth of phi from 0 to theta as you want. And the best choice, the choice which gives you the tightest bound, is to take something where phi varies rapidly when the density is low, and phi is nearly flat where the density is high. So if the density is uniform, like on the left, then you simply take phi, which is a linear function growing from 0 to theta. But if you have a modulated sample, then the system will minimize its energy by twisting, by having a phase which varies rapidly where the density is very low, because there it doesn't cost much to twist, to have a large phase gradient, because a large phase gradient means a large velocity. But if the density is low, you have not much kinetic energy associated to that. But where the density is high, like in the points that you see on the graph, then you should take a flat distribution. Okay, so this is what is hidden behind this Leggett's inequality. If you are still not very at ease with this Leggett's inequality, let me give you an electrical analogy. What we want to measure when we twist the boundary condition is a kind of we want to measure a current that flows in the system when we make this phase twist of theta. The electrical analogy is to compare the system which is on the bottom here, which is what you get. You twist the theta here, and you look at the particle current I theta that appears when you twist the phase by thetas, and GS, the conductance, is simply the h bar over m times rho s, the superfluid density that you want to measure. In the electrical analogy, I just take a medium, and what I apply is a potential difference between the two edges of the sample. I call it U, and I want to measure the current which flows into my system, I equal GU. So I want to calculate the conductance. And the two problems are very similar. And you can actually get a Leggett approach also for the electric problem. Suppose that I give you the following quiz. I take some resistance. I make an array of resistance, like on this graph here. I make an array of resistance. So I have some white boxes here, white resistance that I know. I know their conductances, Gij. And I have some gray boxes that are unknown. Okay? And I want to estimate the conductance between A and B. And I ask you for an upper bound for this conductance. Well, a simple way to get an upper bound is to say, okay, let's replace simply all the gray boxes here by short circuits. Okay? Certainly the conductance will be increased if I remove the gray boxes by a short circuit. Now, if I do that, what do I get? So I get here a series of conductants which are all in parallel. So I can define an equivalent conductant Gi tilde, which is just the sum of all conductances along the column I. And so this is simply n, the average value of Gij over J. And then I end up with what is written here on the left. So I have this equivalent resistance here. So now I have a series of resistance which are all in series, I said. And so the conductance of this series of resistance is just 1 over GAB plus is equal to this 1 over GI and this result. And in the end, the formula that I get, that is the upper bound that I get for my electric conductance, is something which is very reminiscent, as you see, of Leggett's formula, which is written on the upper half here. So if you want to get a simple mind of Leggett's bound, you just think of this set of resistance and you ask yourself, how do I get an upper bound? And you simply replace some of the resistance by short circuits. So there is, I would say, nothing more in Leggett's approach, at least in this very simple classical current approach. So actually, Leggett wrote 2 bounds in his career. The first one I've discussed is this upper bound that he got in 1970, which is, as I said, a variational bound which is applicable to any many-body system. Okay, it can be, again, bosons, fermions, strongly interacting, weakly interacting, mean field, non-mean field. 30 years later, or nearly 30 years later, 1998, he wrote another inequality, which was now a lower bound. This inequality has a more limited range of application. Let's say it's valid if you have a system which is described by mean field, fully condensed system. If not, then you should be very cautious with this lower bound. We had an email exchange with Tony and Willy, and Tony Leggett says that indeed one should be cautious with this lower bound. But for a Bose-Einstein condensate, which is weakly interacting, this lower bound is valid. And if you want to understand it, you can come back to the electrical analogy. So I told you how to get an upper bound. For that, I just said you have to replace the gray boxes by short circuits. Now, if I ask you what is a lower bound for these same circuits, what should I do? You remove them. You open the circuits, and the bound which is written here is exactly the one you get if you replace you remove completely the gray boxes. Okay, so again, if you want to think about in simple terms of these 2 bounds, just think of electricity, and that you will be on a good track. Okay, so I would like to go to the last part of this talk now, which is an experimental test of these bounds. And what I will discuss is a result that actually we just put on the archive, so they are not yet published. Before that, let me say that there have been many experiments and many theory papers on this subject recently. I mean, all the references here are between 2020 and 2025. Initially, the first experiments were done, in our group here and the group of Jan Spielmann on 1D systems, where the 2 bonds actually coincide for mean field system. And then there have been works on more complex systems. There have been many theory papers recently, going further than Leggett's approach on systems where you can have disorder, on Fermi systems, also systems addressing neutron stars. So here you have a few references. And as I said, most of this is motivated by the supersolids that are now produced in the labs. And so there are many papers again on supersolids. So what I would like to discuss today is a 2D system, so not 1D, so the 2 bounds will not coincide, they will give different results. I would like to tell you how we can test this physics. So this is a team which has been working on that. What I will discuss is essentially the PhD work of Franco Rabec, of Sarah Batelier, and of Guillaume Brochier. Okay, so our 2D experiment starts with a 2D Bose gas. So we make a 3D Bose-Einstein condensate. We load it at the single node of a vertical optical lattice, and we compress it using an accordion. So we have completely frozen the vertical degree of freedom. We confine the gas in the XY plane by a box potential. So we work with a 40 by 40 micrometer square box typically. Temperature is very low, below 20 nanokelvin. So we are addressing essentially zero temperature physics. You will see later that maybe we have some residual thermal effect. I told you before that the 2D Bose gas cannot be fully condensed in the thermodynamic limit, but here we are not in the thermodynamic limit. We have a box, and at this temperature, below 20 nanokelvin, we can assume that the system is well described by a single wave function. So it would not be fully condensed if we had an infinite system, but we have a finite size system here. And then we want to apply a modulation of the density to see what is the superhead fraction of our system in the presence of a modulation. So we are not here looking for a supersolid. We are going to break the translational symmetry by hand by applying an extra potential. So here we apply a triangular potential. The period is 6 micrometers, so it's not at all like the optical lattice that we have seen in the previous talk. It is applied. This potential is again created by a digital mirror device. So let me try to get this here. So it is this digital mirror device. So we have a first digital mirror device to make the box, the square box, and then a second one to make the triangular potential. So you see a picture of the atoms here. And we are going to measure the superhead fraction using the speed of sound formulas that I gave you before, Fs equal compressibility kappa times mc square. And we are going to look at the Leggett bounds that we can get from the density profile. And we are going to look whether they are compatible and actually whether we can do slightly better than the work of Tony Leggett also. So how do we measure the superhead fraction from the speed of sound? So we have to measure both the compressibility and the speed of sound itself. So for the compressibility, what we do is we take our sample that we have here, and we apply a small force along this sample. So here the force is vertical on this graph. So it causes a small displacement of the cloud. And in a local density approximation, this corresponds to making the d mu here, and we look how the density responds to this change of d mu. And so we plot the displacement of the center of mass, which is a few micrometers, as a function of the force, and we measure the slope, and kappa is directly from the slope. For the speed of sound, we start a bit in the same way. That is, we first displace slightly the center of mass, but then we remove the force, and the system will oscillate back and forth. We measure the oscillation frequency, and from the oscillation frequency, we have the speed of sound c, which is simply 2L times this oscillation frequency nu. And we do this for various intensity of the triangular lattice, so that we can plot the speed of sound as a function of V0. So this is the result that we get for the speed of sound. So in abscisse, you have V0 measured in units of the average chemical potential. So G, the strength of the interaction, times the average density rho bar. And the y-axis is simply the superhead fraction Fs. So when V0 is 0, we have a uniform system, superhead fraction 1, as expected. And then the superhead fraction decreases when we increase V0. As expected, again, this is what Leggett told us, as soon as you modulate the density, you expect the superhead fraction to decrease. So Leggett gives us actually a bound. So what we do is we look at this density profile and we calculate the bound from Leggett by using the formula I gave you before, this average value of 1 over rho bar and so on. And this is the result that we get from Leggett. So the points here correspond to the prediction of Leggett for this triangular lattice here with the error bars. So the dark zone corresponds to a zone excluded by more than 1 sigma, since we have error bars, of course, on those points. So when you want an upper bound, you want to be confident in the upper bound. So we are going to restrict to the zone which is excluded by more than 1 sigma. So we are going to restrict to that. So we're happy not to have any point in the dark zone here. Otherwise, we would have violated Leggett's inequality. And so I told you that it is a general inequality. We would be in trouble. This is a prediction from Gauss-Piasecki equation, assuming a perfect mean field T equals 0 system. Fine. And this is Leggett's lower bound. Again, the zone excluded by more than 1 sigma. So I remind you, this lower bound is much more restrictive than the upper bound. It is assuming a perfectly T equals 0 system and also a mean field system. So we think mean field approximation in our system is good, but we are not sure to be strictly at T equals 0. So the reason for which we have a few points here, well, 2 points that are inside this exclusive zone may be due to some residual thermal effect. I mean, one would need to calculate the speed of sound with some residual thermal fraction to be sure of that. Yes? Oops, yes. This one here? Yes. Absolutely. Very good question. One with the reason for that, we think, is that when you want to use Leggett's formula, so you have to plug in the density profile. And so we measure this density profile that you see here, but our imaging system is not perfect. We are seeing the first harmonic of the lattice, but we have some missing harmonics. Of course, there is some cutoff spatial filtering of the imaging system. And therefore, maybe the system is a bit more modulated than what we have. And if we say, we have a slightly larger modulation, then the lower bound will decrease more. So we think this is a signature. I mean, this very last point here is a signature that we are not measuring as well as we should the density modulation. Okay, but it's a very good point. Yes, in principle, there should be no violation. Okay, question, can you do better than Leggett's upper bound? I would like to say that the answer is yes. That is, we can be a bit more accurate, can provide better bounds than Leggett's bound, than the bound by Leggett. Actually, we found it by ourselves. More specifically, I should say, Sylvain Lassaben found it and communicate to the rest of the group. But then we discovered that it was already known. I mean, it was a paper by Saslow a few years later after the Leggett's paper. The idea is to take an ansatz, which is slightly more elaborate than Leggett's ansatz. Instead of taking the product of the ground state wave function time a phase factor which depends only on x, now you allow a phase factor that depends on, in this 2D system, on x and y. That is, in your system, you don't assume that the current is flowing only along x, since the velocity is the gradient of the phase. So if you assume that the phase depends only on x, it means that you take as an ansatz a wave function where your current flows only along x. Now, if you take an ansatz where the phase depends on x and y, it means that in your system, you may have currents that flows like that go back and forth, make some oscillation. So you are increasing the variational space, so you are getting a more accurate determination of the true energy of your ground state. And so actually, when you take this ansatz with a phi of r instead of phi of x, then you can show that you get, if you have a mean field system, an exact result. And if you have not a mean field system, this will give, again, an upper bound, but a tighter bound than the one by Tony Leggett. And this is the result that we get when we apply this to our system. We get from the Saslow ansatz the purple points here, which are indeed inside Leggett's upper bound. So we have a tighter bound, as I said. So that's good. I may say a bit more what is below this Saslow approach, because it's not so well known. I mean, there is a nice paper by Blair Blackie on that recently, but it's not so. It has not been used a lot, and so I think it's an interesting result. So as for Leggett's bound, it only requires a knowledge of the density profile, and more specifically, when you calculate the bound, it means that you are actually solving what is called the continuity equation. That is, the divergence of the current has to be 0 in your sample. So the current is the equilibrium density profile that you measure times the velocity, which is unknown. But the only thing you know on the velocity field is that it derives from the phase, v equal h bar over m gradient of phase, and the phase has to satisfy twisted boundary condition. So what you have to do is to solve has to be numeric. You cannot do it analytically. You have to solve this continuity equation with the twisted boundary condition for the phase. You get the velocity field, and then you get the current that flows in the system, and therefore you get the superfluid fraction. What is nice also about this SASLO approach is that it allows to extend Leggett's approach to more complex systems which are non-isotropic. For our triangular lattice, the superfluid fraction was a scalar. It was the same thing along any direction. But if you take a non-isotropic system, you may very well imagine that you make a twist, say, along X, and you have a current which appears along Y, and vice versa. So more generally, the increase of energy that you have to pay when you twist the boundary condition is a tensor that if I twist along X, Y, and Z, the increase of energy is usually this quadratic function of theta I and theta J, where I and J are the Cartesian coordinate. So once you have this tensor, it is a symmetric tensor, so you can diagonalize it, and you get 3 eigenvalues, which correspond to 3 superfluid fractions for the 3 eigenaxes of your problem. And one can show, we do it in our paper that is on the archive, that the SASLO approach actually provides upper bounds for the largest and lowest eigenvalues of this tensor. So if you are in 3D, you have 3 eigenvalues, and the SASLO method gives you a bounds for the largest and lowest eigenvalue. Okay, so I'm getting at the end. So what is the take-home message? So I hope I convince you that superfluid fraction and condensed fraction are different notions that are addressing different properties of your many-body system. And more specifically, I mean, the original part of this talk is that if you take a fully condensed system, which is described by a macroscopic wave function, so long-range order, then the superfluid density is reduced as soon as the density is modulated. And this modulation of density can be there for any reason. The only thing you need to know is rho of x, or rho of x and y, and the reason for which it is modulated is irrelevant. It can be a spontaneous breaking of the transitional symmetry. This is a supersolid, or it can be due to some external potential, like in our experiment, this triangular potential. I also said that there are many ways, or several ways to address the superfluid density. We can measure the speed of sound. We can make this direct measurement of the density rho of xy, and it's also possible to measure the moment of inertia. So with cold atoms, usually this means looking at some specific modes, like the scissors mode, which is a way of looking at the moment of inertia of your system. This is what was used in the experiment by Jan Spinmal recently. And so at this stage, what I've shown is really a proof of principle protocol to measure this superfluid fraction, because I mean, we have a system which is close to mean field, well described by Gauss-Pseudo equation, but all this protocol can be applied, non-modified, I would say, to more complex situation, and that's where it becomes really useful. It can be 2D superfluid, or system with some disorder, or with fermionic gases. And with this, I will stop, and thank you very much for your attention.
Right, John. Yeah, thanks a lot for the wonderful talk. Yeah, we're open for questions.
I will drink some water while you are thinking of your questions.
Stefan.
If you think about a completely different approach to your second idea of having a condensate but no good scattering line zero, then you have zero critical velocity. Does that mean you have zero superfluidity, but still full condensation?
That's, I mean, the ideal Bose gas is really pathological. That is, you can take various definitions of superfluidity. Indeed, if you take Landau criterion, for example, it's not superfluid because the dispersion relation is quadratic and not linear. So moving impurity will be damped immediately. So in a sense, I mean, I mean, we have in our RMP paper with Emmanuel and Willy, we had some section on that. And Willy always say that it's pathological, and I think really you're on the side of people who say that it's still superfluid. No, that
I think if you take zero scattering length, then I mean, although the critical velocity is still super density of the fraction Fs is identically actual to the condensate fraction. Michael Fisher has proved that in a different.
But it's not a very useful definition. I think, Willy, I think you agree. It's not a very useful definition. That is, it's more limiting the order of limit. For me, it has to do with the order of limits. Everything. So, if I take a weakly interacting Bose gas, Fs will be 1, and if I gently turn A to 0, it will remain 1 until it is strictly 0. So then, if I just take the limit, it is 1. If I take an approach of a moving impurity, then it's the velocity is finite of the impurity, and then the system will stop to be superfluid. I think it's really a problem that is not well posed. I think it would be interesting. I don't know any people working on that for the moment, but yes, that would be, especially if you take a non-isotropic system where you would have 3 superfluid axes. I think that would be neat. Yes.
Because that's what typically we have in nature.
Sorry.
What we also typically have in nature.
Yes. And in 3D, you would be sure that you are fully condensed. I mean, you don't have Hohenberg-Mermin-Wagner theorem to tell you that you should be cautious. So then you could be sure that you have fully condensed system and at the same time non-superfluidity or only small superfluid fraction. Yes, but I don't know anyone doing that. I suppose people working on Fermi gases, unitary gas, could imagine doing something like that, but.
I wanted to ask, so you showed there are sort of different ways of measuring superfluid density, right?
Yes.
And one problem I see is that sort of some of the theoretical concepts are kind of hard to realize in experiment, right? So, for example, this phase twist, right? It's not easy to do that in the experiment. So, okay, you showed how to sort of
you rotate.
Well, you rotate.
You rotate. Yes.
It's also not so clear how to do that with a quantum gas, right?
Well, rotating with a quantum gas is feasible. I mean, you can also apply some artificial gauge field and look at the response of your system to an artificial gauge field. I mean, the phase twist can come from some synthetic vector potential. It doesn't have to be a true rotation. So if you have a way, and there are many ways to apply gauge fields, artificial gauge field, then you can do that. Yes.
And so one area where this is relevant are these sort of supersolids that people
yes.
use, right? Very often see sort of like fuel droplets, some
yes.
modulation. My feeling is that people like sometimes actually measure coherence rather than
yes. Yes. Yes.
Right? So like one should really...
Well, it depends on what you want to measure. I mean, first they had to prove that they had a super solid, not a solid. And so the super solid can be some place where you still have coherence. I mean, it's not super fluid, but there is already something super in the fact that you have many droplets and that their droplets keep some phase currents between them, among them. But indeed, if you want to address the fact that they are superfluid, then you have to turn to that. But yes, I mean, there have been some experiments along this direction, especially in Florence. Yes. Vortices, I mean, they can be used in many ways. So I would say, in order to see a vortex array, that is, if you rotate your system and if you want to see a regular vortex array, you need interactions and you test superfluidity. Okay, I would say that. Just seeing isolated vortices doesn't tell you that you have a superfluid system. I mean, by the way, the co-solid-Thouless transition, when it occurs, it means that you have, when it is superfluid, you have some tightly bound vortex anti-vortex pairs, so they are very hard to see. And when you cross the threshold and turn to the non-superfluid phase, to the normal phase, then the vortex pairs break, then you start to see them. So seeing disordered vortices in a sample doesn't tell you that the system is superfluid. It may tell you precisely that you are too hot to be in the superfluid phase. So you should not just say, I have a vortex, I have a superfluid. Of course, to see vortices also, you need some phase coherence, at least locally. So it doesn't tell you that you have a long-range coherence, but in order to have a vortex, you have at least locally, you have to define some phase for your wave function. Otherwise, there is no meaning to saying you have a 2 pi phase winding if you don't know what should rotate by 2 pi. But I would say ordered vortex lattice is a signature of superfluidity. That's what I would say. Really says yes, so I'm.
I just wanted to say, I mean, if you have an ordered vortex lattice with quantized vortices, of course, that and you have this in a two-dimensional ideal two-dimensional Bose gas, then it's superfluid, but there's no condensate.
But you don't get an ordered vortex lattice in an ideal gas.
No,
if you interacting, yes, yes, that's to interact, yes.
Actually, I wanted to ask about sort of solid state systems. I mean, I could imagine doing an experiment like this on a real superconductor, say, where also like image some density, homogeneity,
yes,
apply the same criteria, right?
Yes. Well, that's a good question. I don't know the answer. I don't know any experiment where they would have measured the density. I mean, the density of electrons, say, with STM or whatever, and use that to address a superconducting fraction. I don't think it has been done.
I mean, there's because of the state of a superconductor is, of course, you have a vortex array, but there's no density modulation of the electrons.
But you could probably, but you could texture some material to artificially and then measure the resistance that you have induced by this texturing. That's something that could be done, but I don't know anyone having done that. I mean, if you start to modulate, well, if you modulate the gap in space, I don't know. But again, since no one has done it, I don't want to.
Okay, I don't see any more questions right now. So let's thank John again.
Thank you very much.
Great. Yeah, thanks. And yeah, I mean, feel free to sort of have the coffee here and the cakes, right? And stick around for a bit.